Hello. So I'm going to talk a little bit about H-type foliations today. And these are objects that I had the opportunity to work on during my doctoral thesis. There's quite a lot available in this. This was a collection of talks that I've given. So today I just want to give you some of the underlying theory behind what a sub-Riemannian manifold is, and then give you some of the ideas about what an H-type foliation specifically is, because these are really useful objects as model spaces in more general sub-Riemannian geometry.
And please allow us to bother you if you have any questions, okay? During the
Yes,
talk.
absolutely. 100%. This is supposed to be pedagogical, accessible. If you have any questions at all, let me know. But yes, so I'll actually start a little bit talking about differential geometry just more broadly, just to give you an idea of the context of what we're even studying when we talk about the sub-Riemannian geometry. In differential geometry, the idea is that we've already built up several levels of structures. First, topologically, we have a notion of continuity without any idea what distance or metric or volume is. Then we insist on manifold structures, which is to say a topological manifold is a space. It meets a number of topological criteria, but the important one is that near every point, you can say it looks like, in a continuous topological sense, Rn for some fixed n. Then you introduce smooth manifolds. That is, that these local homeomorphisms, so this local continuity criteria to match with Rn, is actually smooth in some sense. So there should be some sense in which derivatives are well defined. The big step then is to introduce distances. And to do that, it turns out, well, of course, you want something local, but in particular, at every point of your manifold, you have what's called a tangent space. There's a lot of ways to define what a tangent space is, but perhaps the easiest or the most intuitive is to think of it as an equivalence class of curves. But really, what we're trying to get at is describing if you're at a specific point, what are all the different directions that you can move from that point? So the equivalence classes of curves correspond to moving in the direction of some curve. And then to introduce distance, you are basically looking for a function that tells you how long one of these vectors is. What does it mean to have a length in a certain direction? And yeah, that's called a Riemannian metric. And it's essentially what you think of as a dot product in Rn, but it is defined at every point on the manifold, and it has to be defined in a way that is smoothly compatible with all this differential structure I've mentioned in the back. And once you have all of this, you're now doing Riemannian geometry. You can then define the length of a curve, the area of subregions, volumes, well, all of this. Okay, so then some of the tools that we work with a lot, it's going to be particular to my objects, are connections broadly. So a connection just says if you have two vector fields, a vector field means to every point of the manifold you have assigned a vector. So across the whole thing, you have a field of vectors. But if you can operate on the space of the product of vector fields with vector fields to get another vector field that obeys these rules. So this here says that if the first component is a function times a vector field plus a vector field acting on a vector field, it acts linearly. So it's linear in this first component. And in the second component, if you multiply a vector field by a function, that you essentially get a derivative of that out. So it's a derivation in the second component. It's called a connection. Um, this is supposed to generalize directional derivatives. So the idea is that in the first component, that's the direction that you're differentiating. So it should be linear. And in the second component, it's which thing you are differentiating. Thus, it should be a derivation. Anything that does this is called a connection, which is also very confusing sometimes when you're trying to just talk about geometry, because you have to be careful how you use that word. And once you have a connection, you get all these cool notions of curvature. You get tons of incredible results about comparing volumes, comparing distances. The whole plethora of Riemannian geometry sort of falls out from here. And I will mention a priori, the definition of a connection isn't Riemannian. You can do this on a smooth manifold. but it's very natural in Riemannian geometry because of this theorem that either doesn't get a name or some people call it the fundamental theorem of Riemannian geometry that says there is a unique connection that meets these two properties. Um, as formulas, they look kind of gross, but what's happening here is this says if you apply the connection to the Riemannian metric that I was defining earlier, which formulaically always looks like this, means take the derivative of, well, you've taken this inner product, this product of the vector fields, minus applying the connection to each of them. If this whole thing is zero, and you define this other object called torsion. So the torsion of a connection is this sort of anti-symmetrics subtraction minus this object called a Lie bracket. It's a derivation in sort of a natural sense. You should also get zero. And yeah, the fundamental theorem of Riemannian geometry says there is a connection always on any Riemannian metric, a Riemannian manifold, such that both of these vanish. And that's a big deal because it turns out it's really, really convenient to work with in computations. If you're on Rn, it's just the regular directional derivative. It's a very natural thing to work with, which is why I have to make a big deal out of the fact that it's completely unsuited for what I'm going to do with sub-Riemannian geometry. So, sub-Riemannian geometry. The motivation, I think, historically comes from what's called control theory. But the idea is that you want to think of curves on a manifold as describing motion. So it could literally be your manifold is space and a curve is a particle moving through space. Or physicists often like to take a R3n or R6n to be your manifold, where this is the configuration space of n particles, or all sorts of other crazy things. And the idea now is that you're only allowed to move in specific ways. An example we like to give is parallel parking. Technically, if you're driving a car on the surface of the Earth and you pretend that the Earth is okay, you could say that the position on the surface is somewhere on the sphere S2, and your car also has an orientation, so it's also multiplied with the product with a circle S1. The question is, if you're here and you want to get here, how do you do it? And if you've either learned to parallel park or watched enough bad movies, you have to drive forward and then sort of rotate and come backwards, right? Because your car, presumably you're not driving a tank. You can't just move to the side. Um, so yes, the idea is to try to describe a manifold where the motions are restricted. And the way to do that is that at every point you pick a subbundle of the tangent space, which I denote H. It's called horizontal. It's often represented with the letter E too, for whatever reason. And we call a curve such that its velocity vectors are also always in this bundle a horizontal curve. So in sub-Riemannian geometry, we only want to permit horizontal motion, and thus what you actually end up doing is defining a new type of sub-Riemannian metric that is, it behaves just like a normal Riemannian metric on the horizontal bundle, but it's not at all defined outside the horizontal bundle. You simply don't permit those motions to have a definition of length. And then, yeah, so a natural question is, can you just define a horizontal bundle any way you want? No, not at all. It's a typical expectation that if you pick any 2 points in your manifold, you should be able to connect them by a curve. And when I say a curve, I mean a horizontal curve. You want to be able to travel between any 2 points. So there is this beautiful theorem of Shawashevsky back in the 60s that says that any 2 points in a curve, in a manifold, can be connected by a horizontal curve if and only if the distribution is bracket generating. So what this means is, I sort of glossed over this before, but there's a notion of a bracket of two vector fields. This is defined in the standard way that you define differentiation as sort of a limiting process. So when you take the bracket of two vector fields, you get another vector field. We say that the distribution is bracket generating if you take some collection of vector fields in the original distribution, take it brackets of those with each other, and then take brackets of what you got with each other, keep repeating to take these brackets again and again and again. If you can generate the entire tangent space with brackets this way, it's called bracket generating. What this basically implies is if, let's say I have X and Y are horizontal vectors, so they're both in this distribution. If I take the bracket of them and get something out of the horizontal distribution, this is basically saying that if I move in the first direction, then I move in the second one, then I sort of go backwards in the first and backwards in the second, I wound up moving out of the distribution, or rather, I moved in a direction that isn't in the distribution. Now, what I said doesn't actually make sense. It has to be, it's true infinitesimally, but there's a sense in which you can understand that to be the idea behind bracket generating. By the way, this is also called the Hormonder's condition because it relates directly to the equivalent idea that shows up in PDEs. All right, so now I can give you actual definitions. So a standard definition is that a triple M, H, and GH is a sub-Riemannian manifold when you have a constant rank bracket generating subbundle. Constant rank here just meaning that essentially at every point the dimension of H is the same. People do study non-constant rank sub-Riemannian geometry, but it's a whole other thing. Secondly, GH is an inner product on H. So this is what I meant by a sub-Riemannian metric. There is a lot of work done in studying these objects intrinsically, and that is a very active and interesting field. My work with H-tip foliations, which I want to introduce you to here, actually works with what's called the Eulerian method. The notion is that, well, you build a Riemannian manifold that has embedded inside of it in a natural way the sub-Riemannian structure. So this bigger definition here, we say MHG is a sub-Riemannian manifold with metric preserving complement, or an SRMC manifold. It's a mouthful. If first of all, M and G, just ignoring H, is a Riemannian manifold. So you get the whole metric. But then the metric has to split into a product GH and GV. So this is an orthogonal split. And if you drop the V, MHGH is the sub-Riemannian manifold that you care about. And then because you have this orthogonal split, you can say, all right, what is the distribution that is determined by GV? We call that V the vertical space. The idea in this setting is that you can use Riemannian tools on this bigger Riemannian manifold and then make arguments to show that the vertical part doesn't actually matter, that you're looking at information that's really only contained in the horizontal part, the sub-Riemannian part. That's not always possible. There are known to exist sub-Riemannian manifolds that can't have this structure on them. So this definitely does not include all of sub-Riemannian geometry. But as has been shown in my own thesis, the H-tip foliations include a huge array of very important bases, including all of the standard models in low rank, in low step. Okay, yeah, I've basically said all of this. The goal, a large goal in sub-Riemannian geometry is to figure out if there's some Riemannian result, how close can we get to recovering it in a sub-Riemannian setting? Can we get the same thing, or if not, how much broader of a result can we get? Yeah, so this is one of the motivating examples. It's sort of messily written here, but it's interesting, I think. So this is called the generalized Hopf vibration. The idea is you take an odd dimensional sphere and foliate it with circles. So these are actually embedded into S2 n plus 1. Usually I think of S1 over S3. You then have a submersion down to the complex projective plane, which if you are familiar in when n is 1, that means you've got a circle foliating S3 down to CP1, which is itself diffeomorphic to the sphere, the two sphere. Yeah, so having the explicit formula for this may or may not help. I want to show you that in the future. But for now, you can understand that this is also determined by what's called a contact distribution, if you're familiar with that. Yes. So then what's the idea? Like, what do we do with my foliations or more generally, this Eulerian method? You define what's called a canonical variation metric. So for epsilon greater than 0, you define the Riemannian metric G epsilon that looks like this. The motivation then is that if you have epsilon 1, that's the manifold I started with. If you let epsilon decrease to 0, then vectors that are vertical have increasingly long lengths. And the perspective you want to take on this is that most results or most of the concepts in Riemannian geometry come down to studying the shortest curve between 2 points, so-called geodesics. Now, that's a very rough way of describing it, but that is the core of it. We want to understand what curves give us the shortest lengths. So as you let epsilon get smaller, curves that move in vertical directions get longer and longer, approaching infinite length, or we say infinite cost. So it's expected that as epsilon goes to 0, in some sense, this structure begins to look like the sub-Riemannian structure. And it's been well known for a very long time that that's true in the Gromov-Hausdorff sense. That is, the topology of this space approaches the topology of this space in a concrete way. Unfortunately, it's not that straightforward. Okay, so I didn't put the slide here. So a bunch of things go wrong, unfortunately. The first is distance functions. What you would want is that the Riemannian distance function, that is the distance along shortest curves, should go to what's called the Carnot-Theodore metric, which is the distance along horizontal curves. That is true usually, but you have to be more precise. And the precise condition is that we're going to need, well, what I call H-type foliations to guarantee that. There's also other issues. I defined all those notions of curvature before. Turns out all of those just completely fail. For example, sectional curvature, which I think it was a few slides back, it goes to plus or minus infinity, depending on which direction you're looking. So this doesn't allow us to directly bring over the definitions of curvature. So my point being that you have to be subtle. You have to be careful if you're going to use this method. So yes. So here's the first new thing you do. You don't work with Levi-Civita connection. Instead, you introduce what's called Hladký's connection. The Hladký connection is a unique connection that satisfies these collections of axioms. The first thing that's important is metric. So this word metric here means that if you take the nabla and apply it to the metric G, it's still 0. And that was one of the two properties that defined the Levi-Civita connection. The other thing, though, the Levi-Civita connection had 0 torsion. That was that T just disappeared. That can't be true, otherwise this would just be Levi-Civita connection. So instead, we get these 3 conditions that replace the torsion connection, the torsion condition. These two are interesting. There's some sort of symmetry things for the torsion, but the one that's really important to us is that H and V are parallel. What that means is that if you apply the connection to a horizontal or vertical vector, afterwards you will still have a horizontal or vertical vector. So yeah, it's called a Hladký-Bach connection. It's actually well known as the Bach connection. So in terms of the Riemannian Levi-Civita connection, you can write it this way. So this nabla G is the Riemannian connection. And in my setting, I'm actually going to set it up so that this A tensor vanishes. So I'm going to have both of these things disappearing. These disappearing are topological considerations, basically. It's a type of foliation that I'm going to insist we are sitting on. Yeah, and here they are, exactly. So I will always insist that our manifolds are totally geodesic bundle-like foliations, which is just, the definitions are a little bit different, but they're exactly equivalent to these two things vanishing. The last thing we do is we introduce this endomorphism called the JZ map. So for every vertical vector, yeah, you can do it for any vector, but it turns out we just have it 0 for the ones that are horizontal. So for any vertical vector, I define JZ XY to be equal to Z against the torsion of XY, where this angle bracket is also another notation for the Riemannian metric. Yeah, and then you get it pretty quickly. If Z is horizontal, this happens. If Z is vertical and X is horizontal, you get another horizontal vector. The point being that now J turns vertical vectors into endomorphisms of horizontal vectors. And specifically, it satisfies this. Or rather, we insist that it satisfies this condition here. If you have sub-Riemannian manifold of metric complement, that is a totally geodesic foliation bundle-like metric. So that means those topological considerations are taken care of, and the formula for the Bach connection is nice. V is integrable. Turns out this is redundant. You don't need this condition, but it's nice to say it. And it's a fancy way of saying that the leaves of the vertical directions are leaves of a foliation. But then this is the interesting condition, that jzx, jzy always gives you the magnitude of z squared xy, which you might recognize as another way of saying, I want to skip ahead and find the condition here. Well, it's another way of saying that jz is effectively, pointwise, a complex structure. That is, j squared is negative the identity. That's true when z is a unit length vector and we're talking about pointwise. So globally, that's a little bit more complicated. But this is essentially the idea. We are in some way introducing some sort of analog of complex analysis pointwise on these tangent spaces. So yeah, for the sake of time and because I want to, give us a little bit of break, I introduced a lot of information, thought I'd give you a short list of key examples. So hopefully I can convince you that despite all of these conditions I'm throwing out here, that this actually has a lot of useful, interesting examples. So H-type groups, the Heisenberg groups, Hopf and anti-de Sitter fibrations, which are low-dimensional models of well, people claim the universe sometimes, but at the very least, they're curved models of these things. K-Tantek manifolds are just weaker generalizations of these things. Since you have these, it's not surprising that you get Sasakian and 3-Sasakian ones, quaternionic spaces. It is surprising that you get twister bundles. At least I think is surprising. So what this means is that you take one of these things, a quaternionic group, or even just a contact manifold, and then look at the sphere bundle over it. That is the set of unit vectors in its tangent bundle, and make that its own manifold, if you're familiar with the idea. So we can talk about it more in the future. But yeah, this is just a small zoo of H-type foliations. And the last thing I wanted to tell you, just to give you a taste of what we can do with this, is let's see, where is it? Here we go. So in Riemannian geometry, you get these sort of fun statements that say, if you know the Ricci curvature is greater than kappa, there's some dimensional constant in here, but this basically says that the Ricci curvature is greater than constant kappa, then the Laplacian of the distance function will always be bounded by one of these functions, depending on whether kappa is greater than 0, equal to 0, or negative. It's called a Laplacian comparison theorem. And you also get directly from that an estimate on the diameter when you have a positively curved space. We managed to do the same thing. So this is a really messy way to present it. Where is a nice one? Yeah, I'll give you this. So if you have, if you're in the same setting with an H-type foliation, and you know it has a certain structure that makes the J maps a little more rigid, you get these upper bounds on the Hessian, so equivalently an upper bound on the Hessian, where the new thing is this, they call them F-Riemannian and F-Sasakian. It's this here, it's these functions. You know that notice that F-Riemannian is exactly the functions I showed on the last slide, the ones that show up in Riemannian geometry, and F-Sasakian are these crazy looking things. But if you actually compare the functions, they're basically they have the same structure. They behave the same in the small and large limits. It's just in the middle. These new Sasakian ones are a little bit weaker. They take a little bit longer, but roughly they give you the same sort of information. Anyways, so yeah, there's a lot more that could be said about that. There is a brief introduction to sub-Riemannian geometry and H-type foliations. And thank you.
Yeah, thanks for the wonderful introduction of the sub-Riemannian geometry, especially the H-type, which are the models. So are there any questions, comments, discussions, or feedback whatsoever?
Yes, I have one basic question because I am also a beginner of this topic. So I can't remember the exact way of addressing that structure, but whenever we study the sub-Riemannian structure, the induced from the whole the Riemannian metric, then in your definition, you mentioned the orthogonal, the vector bundle formed from the structure. So it's
I'll look for the slide, but go ahead.
Yeah. So yeah, metric preserving the complement. So is this orthogonal complement becomes the smooth vector bundle automatically?
So the way we're doing it here, we're actually just saying, okay, we're assuming that this sort of structure exists. It's
Mhm.
not generically possible. So there are plenty of examples of sub-Riemannian manifolds that you can't do this at all.
Okay. Mhm.
And I can imagine that you would be able to find examples where you'd have issues with smoothness. But like most of the constructive examples of sub-Riemannian manifolds are, for example, contact manifolds.
Mhm.
And in that case, yes, it is automatically a smooth vector bundle. In fact, it's a foliation.
Yeah. Okay. Yes. So, but it's not the general the possible in any case.
It is definitely possible to construct sub-Riemannian manifolds for which this can't happen.
Okay. I see.
But they're, to the best of my knowledge, they're pathological in the sense that you have to go out of your way to construct them that way. The vast majority of sub-Riemannian manifolds that people work with or are interested in
Mhm.
arise from having a Riemannian manifold and saying, oh, hey, I only want to move in a subset of directions there. So then
I
they
see. Mhm.
pick the horizontal distribution, but that means that naturally they secretly had the vertical structure already there. So I don't want to minimize it. It's very important to have intrinsic constructions and an intrinsic understanding of these spaces. But I think
Okay.
it's very valid to
Mhm.
work with this extrinsic version.
I see. Mhm. Well, thank you. Mhm.
Of course, it's a great question. It's a lot of there's a lot of debate back and forth as to best methods in this setting.
Mhm. Yeah. Thank you for your response. Mhm. Yeah.
So yeah. Any other comments or questions? So I'm not sure that we need to take a break at this point, so maybe we can just jump into the next presentation then. So how about the prepare for the next talk?
Absolutely. Thanks again for the opportunity to present. I'm looking forward to the rest of this.
Yeah, thanks for the great talk.
All right. So let me just try share my screen. I've already uploaded this note to the Dropbox folder. So can you see my screen?
Yes, we can. Thanks.
Okay, so yes, as I wrote in my email, at first glance, this topic seems have nothing to do with sub-Riemannian geometry, but the goal of all my presentations is to introduce some interesting result from the non-commutative geometry, which applies to the settings of the Riemannian geometry. And I'd like to seek for the possibility of the generalizing this result in the settings of the sub-Riemannian geometry, or concretely to the Heisenberg group or the contact manifolds or the other more example mentioned in the Gianmarco's presentation. So, but in order to introduce the results from the non-commutative geometry, it's inevitable to introduce the result from the functional analysis. So for today and for the next one or two, my presentation, I will only discuss about the necessary functional analysis result to introduce the result in the non-commutative geometry, and I will explain you later on how to connect this result in the functional analysis to the geometric data which comes from the Riemannian metric or the other data from the geometric settings. So anyways, I think the best one to start with is the CONN'S Trace theorem. It's one of the most fundamental result in the non-commutative geometry, introduced by the Professor Alan Kohn in 1988. Okay, so and this is not exactly the first version introduced by Professor Alan Connis. This is the version refined by the other scholars about 10 years ago. Okay, so I think there are many the notions or which is not familiar to you, so I cannot explain all of them at once by today, but I will explain the notions used in this the theorem, each of them for my presentation. Okay, so my goal today is to explain the meaning of this space used in this theorem. Okay, and let me briefly tell you the meaning of this theorem. Okay, so here I will only work on the Rn for the next several seminars. This theorem also holds on the more general, for example, the compact manifold, but as Dr. Cho emphasized to the work on the concrete examples, I think it would be better to just start working on the Rn first, and I will tell you the same result to still hold on the general spaces. And my first goal is to start generalizing this theorem, for example, on the Heisenberg group or the contact manifold. Anyway, okay, so here I say the P is a compactly based the classical pseudo differential operator of order -n. The compactly based is just some sort of the technical assumption, so I will omit explaining this notion. And the classical pseudo differential operator is some sort of the generalization of the notion of differential operator on the Euclidean space. But here the pseudo differential operator, we allow that, as we already know, the differential operator has a notion of symbols associated with it, and the symbol of the differential operators are the polynomial. So the differential operator of degree m has a symbol of the polynomial symbol of degree m, but the pseudo differential operator, the definition of the pseudo differential operator can be obtained by the generalizing the notion of symbol to the more general functions than the polynomial. And we, in the theory of pseudo differential operator, we allow that the symbol of the pseudo differential operator has infinitely many homogeneous parts. So the pseudo differential operator can have the homogeneous part of degree, the negative integer degree, and so let the P be such kind of operator which has the order -n, so it has a degree -n homogeneous parts, and we define the numerical invariant associated with such pseudo differential operator by this way, integrating this the degree -n principal part of P. We integrate it in X on Rn, and we integrate this function in Xi on the unit sphere. And in the case of the compact Riemannian manifold, this integral is replaced by integrating on the unit cosphere bundle, but I will discuss such thing later on. So we associate the numerical invariant associated with a given the pseudo differential operator satisfying this condition. And well, there is some sort of the subspace of the space of the bounded linear operators on L2 space of Rn. So this is the subspace of the bounded linear operators on the Hilbert space. And it can be shown that this kind of pseudo differential operator belongs to this subspace I will introduce today. And I will also explain the next time that there are many kind of the very nice linear functionals, the trace on this space, and we can evaluate this trace on P, and these two numerical invariant exist. So why is this theorem very important? As I will explain next time, this trace on the left-hand side can be defined just by using the purely spectral data of the given pseudo-differential operator P. And whenever we apply this theorem to this pseudo-differential operator, here the MF is the multiplication operator given by a function f, and here delta is the Laplacian, and 1 plus delta minus n over 2 is defined by the technique called the functional calculus in the functional analysis. And it can be shown that this operator forms a pseudo differential operator of order minus n. I will explain all these things later on. And so if we apply the above theorem to this operator, then whenever we try to compute this integral for this operator, then we recover this integral. So the right-hand side is the integration of f times some constant. And as I told you, the left-hand side can just be defined by using only the spectral data of the given operator. So what is the meaning of this CONN'S Trace theorem? This is the purely spectral data discretion of the integration on the manifold. Okay, so this connects the spectral data of the operator on the Hilbert space to the integration on the manifold. Okay, so I will explain you how to connect this to the data, which seems completely irrelevant at first glance. But for today, I will focus on explaining the meaning of this space L, the sub 1, infinity, the domain of this trace used in the left-hand side. So the questions so far? I think this is most of you are quite unfamiliar with this kind of the direction. So if you have any question, please interrupt me.
Maybe I'll ask just a quick question. This
Yes,
integral that shows up in the formula for the residue, is this somehow related, or maybe a generalized version of the Fourier transform?
Generalized version of Fourier transform?
Yes. Or am I just a little off basis?
No, as far as I know, to the best of my knowledge, I don't know how to connect this integral to the Fourier theory.
That's okay. But you did say that on a general or in a more general setting, it'll need to be done over a cotangent bundle.
So this whole integral is replaced by the unit co-sphere bundle. So here the fiber of the unit co-sphere bundle is is the unit sphere inside the cotangent, each cotangent space. Yeah, with respect to the reduced Riemannian metric on the cotangent bundle from the Riemannian metric.
Okay. Well, I think that's particularly interesting from a sub-Riemannian point of view, but we can discuss that when it comes up. Thank you.
Okay, so let me tell you some necessary functional the analysis, the preliminary materials to explain all the ingredients of the theorem. So I will focus on the left hand side for today and for our next seminar. Okay, so let's fix some the notations here. I'll denote the separable, the infinite dimensional Hilbert space over C by this calligraphic H, and of course it's equipped with the inner product, and I adopt the convention that is linear in the first variable and the conjugate linear in the second variable. Of course, I think you already know that the Hilbert space automatically becomes a Banach space with respect to the induced norm from the inner product, and we say that the linear operator between Hilbert space is bounded. Of course, is equivalent to say that it's a continuous linear operator if there is a constant satisfying this estimate, and using this estimate, the smallest constant satisfying this estimate can be used to define the norm on the space of bounded linear operators between these Hilbert spaces. Okay, and for the bounded linear operator, we can define the notion of the resolvent set, which is the subset of the set of complex numbers defined like this. So rho T is the collection of complex numbers such that the complex number lambda, such that T minus lambda is an invertible operator from H to itself. Okay, and here the lambda here is the shorthand notation of this operator, lambda times the identity operator. So T minus lambda makes sense as a bounded linear operator from H to itself. Okay, and it can be shown that this rho T is an open subset of C. Thus, its complement is closed subset of C. And we call that the complement of the resolvent as the spectrum of T. So the sigma T is the set of complex numbers such that the T minus lambda is not invertible. Okay, and we say that the element of the spectrum is an eigenvalue of T if this is not invertible. And one should beware that in the case of the infinite dimensional Hilbert space setting, the complex number is an element of the spectrum and the complex number is an eigenvalue are not equivalent notions, because one can find an invertible and injective operator because we are in the infinite dimensional setting. Okay. Well, then what one can easily see that this is exactly the typical example of the bounded linear operator, which does not have any eigenvalue. So in the Hilbert space, the infinite dimensional, the Hilbert space setting, it is possible to find the bounded linear operator, which does not have any eigenvalue sitting inside the set of the spectrum. Okay, so why do we start to discuss the spectrum or the eigenvalue? Later on, I will tell you that these are the collection of numbers, and for a certain kind of bounded linear operator, we can extract very nice sequence from this the spectrum set, and we will build the sort of the numerical invariant from that the sequence from the extracted from this the spectrum. So that's how we build the linear functional from the bounded linear operator on the left-hand side later on. Okay, so from which the bounded linear operator we can obtain a nice sequence to compute some sort of the numerical invariant. Well, we need the special kind of the bounded linear operator, which is called the compact operator. We say that the operator is compact if the closure of the image of the unit ball is a compact subset of H, and the space of compact operator will be denoted by the calligraphic K, and there are the equivalent the description of the notion of compact operator. Well, the T is a compact operator if and only if it's a limit of finite rank operators, and it is also equivalent to say that for any orthonormal basis of H, then, well, if the En is the linear span of the first n vectors of this orthonormal basis, and if the En perp is the orthogonal complement of En in H, so this is an infinite dimensional subspace of H, and if we take the restriction of T on this infinite dimensional subspace of H, and take the operator norm of this guy and take the limit n goes to infinity, then it converges to 0. So what is the sort kind of the heuristic meaning or the description of the compact operator? In the case of the compact operator, it can be approached by a sequence of the finite rank operator, which means that if we forget some information of some sort of the finite dimensional subspace of the given Hilbert space, then the remaining orthogonal complement part, on that orthogonal complement part, then we can make the operator norm of T on that orthogonal complement part as small as one desire. Okay, and the shift operator I mentioned above is one of the typical example of the non-compact operator, which is not an identity operator, and also the identity operator on the Hilbert space is not the compact operator. Okay, and one of the basic result concerning the space of compact operators is that it forms the closed subspace of LH, and it forms a two-sided ideal of LH, and it's closed under the Hilbert space adjoint. Okay, so if T is a compact operator, then it's a Hilbert space adjoint. T star is also the compact operator. That's the meaning of the notion, the star ideal. Okay, so it forms a very nice subspace of the LH, and also the spectrum of the compact operator has a very nice property. The spectrum of T consists of 0 and a countable set of eigenvalues of T. So 0, if 0 may be or may not be the eigenvalue of T in this case, but all non-zero element of the spectrum should be an eigenvalue of T. Okay, so for the non-zero spectrum of T, in the case of compact operator, we don't need to distinguish the to being the element of the spectrum and being an eigenvalue of T. In the case of compact operator, for the non-zero operator, the being spectrum or the being the eigenvalue, they are the exactly equivalent discretion. And if the spectrum set admits a limit point, then the only possibility is the origin of the field of the complex numbers. Okay, so and it is also well known that for all the non-zero spectrum of T in the case of compact operator, then they should be the eigenvalue, and there is no eigenvalue with infinite multiplicity. All the non-zero eigenvalue should have the finite multiplicity. What do I mean by the multiplicity? Here, the multiplicity means that the dimension of the eigenspace associated with lambda. Okay, so based on these two theorems, we can obtain a very nice sequence from any compact operator. Okay, so as the spectrum set of the compact operator forms a countable set of eigenvalues, okay, then we can arrange it with this order. It's the absolute value of that the sequence is decreasing. Okay, and so the sequence satisfying this condition is called an eigenvalue sequence of the compact operator. So what do I mean by eigenvalue sequence? The absolute value of this sequence should be decreasing, and all non-zero entries of this sequence should be the eigenvalue of T, and we repeat the non-zero eigenvalue according to its multiplicity in the sequence. Okay, and if there is only a finite number of non-zero eigenvalue, the finite number n, then we define the eigenvalue sequence of T in this way. Okay, so we arrange we put all the non-zero eigenvalues in the first n entries of this sequence according to this order. Okay, and one should be aware that whenever one uses the notion of the eigenvalue sequence of a compact operator, here I use the indefinite article on here because the eigenvalue sequence of T is not unique, because if one rearrange the eigenvalue sequence, one can still obtain the eigenvalue sequence satisfying all the same condition. And here is a simple example of the two eigenvalue sequences correspond to a given compact operator. Okay, so to consider the finite rank linear operator defined like this. Here I think I made a mistake. This xn should be replaced by en. Sorry about that. But anyway, this is given an orthonormal basis of a Hilbert space. For the first entry of this orthonormal basis, I send it to the E0 itself, and I send E1 to minus E1. And for all other En, I assign 0 to them. Then, of course, this forms a finite rank operator of rank 2. And there are only two eigenvalues, the 1 and minus 1. And both of these sequences are eigenvalue sequences of A, because if we take the absolute value of this sequence, it satisfies the first condition, and all the other conditions are also satisfied. So the eigenvalue sequence of T is not unique. The one can form the various eigenvalue sequence of the given the compact operator by rearranging the given the eigenvalue sequence. Okay. So any questions so far?
Yeah, this looks so natural, innovative if I imagine the complex plane, and I just need to look at the magnitude, so that I just need to make the maximize the radius in the beginning, and I just need to shrink slightly, so it is very natural to have the many such sequences. So it definitely makes sense.
Yep, exactly. So actually this is the reason why we consider the compact operator, the operator which can be approached by a finite rank the operator. So by combining all these results right here, one can easily see that if we denote the space of the complex valued sequences converging to zero like this is of course a vector space, and the eigenvalue sequence of a compact operator always belongs to C0. So due to the very definition of the eigenvalue sequence, we can always say that the limit of this eigenvalue sequence as the index j goes to infinity is 0. Okay, so
can I ask about the rearrangements?
Yeah.
So I know you're saying that we have to be careful about rearrangements, but just to clarify, to make sure I'm fine with this, you can only have rearrangements with of the eigenvalues with the same complex modulus. So you're really just rearranging the order of eigenvalues on the same say circle in the complex plane.
Yeah, exactly. So that's the way of forming the other eigenvalue sequence from the given the eigenvalue sequence. Exactly. Okay. So any other question? Okay, so let me briefly tell you about the notion of the functional calculus, because in order to define the sequence from the given compact operator, we will use later on. It is necessary to define the notion of the absolute value of the given linear operator. So for the given linear operator, as in the case of the usual the linear algebra, we say that the linear operator is normal if it is commute with its own Hilbert space adjoint, and the compact normal operator share the nice property as in the case of the normal square matrices in the linear algebra. The compact normal operator is diagonalizable. So briefly saying it means that the compact normal operator can be written as an infinite sum of the rank 1 projections on the linear on the given the Hilbert space. So the rank 1 projections times the eigenvalues in front of it, and by using the diagonalization for any function on the spectrum of a continuous function on the spectrum of the given the compact normal operator, we can make sense of the operator ft like, so it's kind of the generalization of the evaluating the matrix to the function or the polynomial. Okay, so by using the spectral theorem of the compact normal operator, we can make sense of this operator ft by using the diagonalization. Well, imagine that in case of matrix, once you diagonalize given the matrix, then this kind of the matrix evaluated in function can be defined by the evaluating each eigenvalue on the diagonal entry to the function f. So the business can be done in the infinite dimensional Hilbert space case. Okay, and so let the T be a compact operator. Then of course this become a positive compact operator. What do I mean by positive? Well, the positiveness means that its spectrum belongs to the positive real line. And here the square root is a continuous function on the positive real line, which contains the spectrum of the given operator T star T. Okay, so we can evaluate T star T to the square root function by using the procedure explained above. So this operator is called the absolute value of a given compact operator. And this absolute value of T is a positive compact operator. Okay, and as it's a positive operator, all of its eigenvalues are the positive number. Okay, so if we consider an eigenvalue of sequence of this absolute value of T, then we call an eigenvalue sequence of T a singular value sequence of T, and it's denoted like this. So in other words, we define the singular value of sequence T, the jth component of the singular value sequence of T is the jth component of the eigenvalue sequence of the absolute value of T. And it makes sense to define like this because due to the nature of the eigenvalue sequence I mentioned above, in general, an eigenvalue sequence is not unique, but in case of the positive compact operator, then all the eigenvalues are the non-negative real number. So if we try to obey all these conditions in the definition, then we can say that the singular value sequence of the given compact operator is unique. Okay, and let me skip this example because I think it's not important for today. Okay, so right, so now we have the notion of the singular value sequence of the given compact operator. Okay, and okay, so I think I need at least to explain the notion of the decreasing rearrangement. Okay, so for a given sequence which converges to 0, we say that this new sequence, we take the permutations of the indices and take the absolute value of the given sequence, and we say that this sequence is a decreasing rearrangement of A. If we take the permutation of the indices and take the absolute value, then it becomes exactly the decreasing sequence. So we call this sequence a decreasing rearrangement of the sequence A, which converges to 0. Okay, and we will denote the decreasing rearrangement of a given sequence A by mu A. Okay, right, and subspace J of C0 is called a Culkin space if it satisfies this condition. If A is an element of this sequence space and decreasing rearrangement of B is dominated by a decreasing rearrangement of A, then B is also an element of J. Okay. All right. So what is the typical example of this Culkin space? The most typical example is the small LP space. Okay, so this norm of the small LP space seems a little bit different from the usual definition you learned from the analysis course, but it still gives us exactly same norm after we do the decreasing rearrangement of the given sequence A. So the small LP space is the typical example of the Culkin space, and the weak LP space, which is denoted by small l sub p comma infinity. And if the sequence satisfies this decaying property, so here the mu ja is of course the jth entry of the decreasing rearrangement of the given sequence A. If the sequence A satisfies this decaying property, we say that the sequence A belongs to the small LP comma infinity space, and the sequence A is a weak LP class sequence. So these are the typical examples of the Culkin space, Culkin subspace of the sequence space C0. Okay, all right, and consider the two-sided ideal of the compact operators. Okay, in that case, we can construct a so it seems inevitable to explain the above the example. Okay, right. So given
So
the
sorry.
sequence in
So over here, I
Mhm.
just want to be clarified for just the C0. What is the set C0 here?
the space of the sequence is converging to zero as j
Okay,
goes to infinity.
Thanks. Got it.
Yeah. Yeah. So for such sequence, we can define a linear operator on the Hilbert space associated with that sequence by fixing an orthonormal basis of the Hilbert space and assign each element of the orthonormal basis in this way by using the entry of the sequence. Okay. Then due to the assumption that the A is the sequence which converges to zero as j goes to infinity, it can be shown that this diagonal operator given by a C0 sequence is a compact operator. Okay, all right. And the last thing I'm gonna explain you today is the notion of the Culkin correspondence. Okay, so let's consider a two-sided ideal of the compact operator. Okay, then to this two-sided ideal of K, we can assign a sequence space J in this way. Okay, so J is a collection of sequence in C0 such that a diagonal operator associated with A belongs to a given two-sided ideal. Okay, so in this way, we can associate a sequence space to a two-sided ideal of K, and conversely, given a Culkin space inside C0, we can associate a two-sided ideal, a subset of K, by this way. So given a subspace J of C0, okay, consider the set of compact operators such that its singular value sequence belongs to the given Culkin space. So we can construct the subspace of compact operators from the given Culkin space. And there is a very big theorem that this correspondence is exactly inverse to each other. And this correspondence is a one-to-one correspondence between Culkin spaces in C0 and the two-sided ideals of K.
I have a question.
Yeah,
And maybe
please.
the theorem answers it, or maybe it's actually matters. So in your definition of the diagonal operator associated to a sequence A, you said that you need to choose an orthonormal or orthogonal basis for the Hilbert
Yeah.
space. If you choose a different basis, will that change the correspondence that appears in the theorem?
Yes, thank you for your question. Actually, that's not trivial at all, but once you try to find the textbook, it can be shown that the correspondence or definition does not depend on the choice of orthonormal basis.
Okay,
so
good. I would hope so, but it's worth asking.
Yeah. So of course it should be checked that if well the one still for example, so one still gets exactly the same Culkin space if we use the diagonal operator associated with the orthonormal basis, but I can say that it holds.
Okay, great. Thank you.
Yeah, well, thank you for the good question.
Yeah, so I also have a question. So I'd like to start from the proposition 2.7.
Okay.
So I think I need to ask this for understanding non-commutative algebra, which actually really means in this context. So in order to talk about the idea, let me try to be really silly. So in order to talk about the idea, then one need to have the multiplication and the addition.
Yes, of
What
course.
are them here?
Well, the addition is just the usual the addition of the linear operator on the vector space. So the sum of the two bounded linear operators forms another bounded linear operator with the natural definition. And here the product is given by the composition of the linear operators on the given Hilbert space H.
So that's why we do not have the commutativity any longer in such a context. So
yes, so this is a non-commutative the sub-algebra of this algebra. So because we are dealing with the linear operator, we cannot expect the commute in general.
Maybe I can also just extend the question a bit. Because we're working with compact and bounded operators, this is why we don't have to worry about domains of definition for composition or any of that. Like we don't have to, we're not concerned at all about the domain on which these things are defined.
Yeah, because all the domain and the codomain of all the linear operators are this Hilbert space H. So this well all the operators I'm talking about are the endomorphism of the vector space H. So we can composite them in any way around.
Okay. Does this theory start to extend to unbounded operators, and then you have to start thinking about that, or is this all fall apart?
Well, in the case of this, how can I say it? Well, we can of course discuss about the spectrum of the unbounded operator. For example, like the Laplacian on the compact manifold is the unbounded operator on L2 space associated with the Riemannian the measure given by the Riemannian matrix. So we can discuss the spectrum of the unbounded operator, but the notion of the compactness, well, in the case of the unbounded operator, then the spectrum does not usually have the good behavior like this. So considering the notion of the compact operator in the space of unbounded operator does not make much sense.
Great. That answers my question. Cool.
So let me try to interpret this correspondence in my really silly manner. So I will just consider the finite dimensional vector space, and I just have so I want to interpret this theorem as nothing but the generalization of the singular value decomposition from the elementary linear algebra in a way that if we have just the n by n matrix, then we can consider it's called by A, and we have the A transpose A, so that we can just the spectral theorem, so that we have corresponding the eigenvalues. Then each eigenvalue we have just like for each lambda times just the identity map. So it looks like the idea here is just generated by those identity times that eigenvalues. Am I right? So that just gives the the one-to-one correspondence between just a spectrum. Right, spectrum and the just for each eigenvalue. So we just create the spectrum times the identity, so that we have just correspondingly the bounded linear operator. So that seems
okay. So in the case of the linear algebra on the finite dimensional the vector space, one can get the useful invariant of the linear operator by using the eigenvalues. If we take the sum of all of them, then what we get is the trace, for example. And well, if we take the product of all of them, then we get the determinant of the given linear operator. But in the infinite dimensional case, it's not as simple as in so the finite dimensional space, because as we obtain here we are using the singular value sequence instead of the eigenvalue sequence. And well, in the infinite dimensional case, we have the infinite sequence, the infinitely many numbers. So we cannot just simply taking this, for example, the sum of all of them to obtain the trace of the given linear operator on the infinite dimensional space. So to obtain or extract a numerical invariant from the spectrum, the sequence or the eigenvalue sequence or the singular value sequence of the given linear operator, then one should have the certain kind of the summability condition, or at least the certain decaying condition to guarantee the well-defined this of the numerical invariant the linear functional, extracting the numerical invariant from the singular value sequence or eigenvalue sequence of the given linear operator. So the idea of this Culkin correspondence is that to give the one-to-one correspondence between the summability property or the decaying property to define to classify the linear operator. So we define the notion of the Schatten P ideal of compact operator, whose singular value sequence exactly belongs to the small LP space. Okay, and we define the notion of the weak Schatten P ideal of compact operator as the set of compact operators whose singular value exactly have this decaying property. Okay, and if we in particular, if we set the P equal 1, then L1 infinity, which is called the ideal of a weak trace class operator, is the space used on the left-hand side in the definition of the CONNE'S Trace theorem. So in order to define linear functional, the well-defined linear functional from the singular value sequence or the eigenvalue sequence of the given compact operator, then as we have the infinitely many entries in that sequence, one should have some sort of nice summability, or at least the decaying property, to define some sort of the well-defined trace or the linear functional on that space of operators. So this is the space where I will construct this the so-called normalized trace on the space of operator. This does not make sense for the general compact operator or the more general the bounded linear operator, because in order to define this notion of trace on the left hand side, we exactly need this kind of the decaying property, as I will explain you next time.
Yeah, thank you very much for the detailed
Yep.
explanation.
Yep. So it took longer than I expected, and sorry about that. And I stop here for today. And thank you very much for your attention.
Yeah, so I think for today's talk, we might just finish over here because we already spent a amount of energy, so that we will just start the seminar after 2 weeks. How about it? And I'd like to make more conversation with John Marco and so also Kihyun, just the three of us for the direction of the seminar, and also I'd like to share something in like the informally, so without the record.
Okay. Okay. So let me just stop sharing my screen.
Okay. Yeah. Thanks for today's our presentation. So we'll meet after 2 weeks, and yeah. So that's it for today. Yeah.
Actually, concerning the seminar, you mean the February 16th, but I'm sorry about that. But it turns out that the mentor just informed me to go some sort of the event in Brussels on the 16th. So unfortunately, I'm not available on the 16th, and for the 23rd, I also noticed that the Gianmarco is attending the conference in Potsdam with me. So I think both of us are not available also in the 23rd.
So then
I will be attending conferences back to back for about 4 weeks in a row. So I will attend this from the conferences when it's necessary. So if that doesn't work for you, it's okay. But if I had to skip for conferences, I'd be unavailable for almost a month and a half.
Yep, so, I'm also available to attend during the conference, so it's up to you.
But you'll be there at Potsdam?
Yeah,
then
I'll be at Potsdam.
Let's skip the meeting after 2 weeks, and we will just try to adjust the schedule. How about it? But let's not after 2 weeks. So it might be either next week or even next week or 3 weeks later, as you said, during the conference, but we can just also postpone the March. So let's just adjust the schedule later on. I think it's not a big deal.
Then how about just meeting at the March 2nd, 4 weeks later? Sorry about that.
If you want that, yeah, that's definitely okay, at least to me. But I'd like to make some conversation between two of you. Okay, I mean today.
Yeah.
So let me just.
Okay, see you in a month then.
Yeah, see you.
And have a nice day.
Okay, bye.
Thanks for attending.